Now, I'm here at Lightwater Valley today for my science project, and I'm hoping to find as many different solids, liquids and gases as possible. So, let's go.
Wherever you go, you're surrounded by objects made of different materials. Scientists like putting things into groups, and one way of categorising materials is to split them up into solids, liquids and gases. Solids are easy to spot.
This metal frame is definitely a solid. Now, it's hard and staying put.
In science, a solid is something which has a definite shape and takes up a fixed volume.
Now, the most obvious liquid has got to be water. It's run it and it changes shape a lot.
Liquids change their shape easily. They simply take on the shape of their container. The most obvious gas is air. Although most gases are invisible, you can sometimes see them inside things.
This thing is full of air. Now, gases can be squashed and are very light.
Just like liquids, gases take on the shape of the container they're in, but they behave quite differently.
Is it on? Yeah. OK, so I've got two footballs here. This one is full of air. It's light and it's got loads of bounce. And this one is full of water.
Solids, liquids and gases each have different properties which make them suited to different jobs. Solids are often hard and strong. For instance, wood and steel are good for building things with. So why use a liquid in these rides? And why are these dinghies full of air? Solids, liquids and gases behave very differently from each other. Scientists think it's because the particles they're made up of are arranged differently. The theory is that everything is made up of millions of tiny particles, far too small to see. This can is made of solid aluminium metal. Its particles are packed tightly together. They're held in a fixed arrangement and hardly move. Because the particles are held in place, it has a definite shape unless you're strong enough to change it. Squash all the air out of the can and you're left with a lump of metal. But the metal itself can't be squashed. Its particles are already as tightly pushed together as possible. It's a solid. The drink behaves quite differently. The particles are still held closely together, but they aren't in a fixed arrangement. Instead, the particles tumble over each other. Which is why a liquid takes on the shape of whatever container it's in. Like a solid, it's impossible to squash a liquid. This bottle's full to the brim. It can't be squashed because there isn't any space between the particles. A liquid can't be compressed. This bottle's full of air. The gas inside can easily be squashed into a smaller space. The particles in a gas aren't held together, and because there's plenty of space in between them, they can be pushed closer to each other. Gases can be compressed. But not every substance fits so neatly into one of these three categories.
All things, all stuff, all bits and bats, all clutter and clatter, it all amounts to three things, the three phases of matter. Liquid, solid, gas. Me, my nails are solid, but blood, sweat and tears are liquid. And as for the gas, well, the less said, the better. Gas. All things, all stuff, all bits and bats, all clutter and clatter, it all amounts to three things, the three phases of matter. Liquid, solid, gas. So what's double whipped cream then, besides gorgeous. It doesn't feel like a solid. It looks more like a liquid. Squirts out of a can and sounds like a gas. Definitely gorgeous, perfect and sweet. But whatever it is, it's great to eat. So what's jelly then? And peanut butter? What's sand in my hand? What's mud in the gutter? What's toffee cream? What's ice cream? It's enough to make a grown man scream! But all things, all stuff, all bits and bats, all clutter and clatter, it all amounts to three things. The three phases of matter. Liquid, or solid, or gas.
Solids don't always stay solid. Heat up these lumps of wax and see what happens. The fact that wax melts means a shapeless lump can be made into a lifelike model with crafted features. Behind the scenes at Madame Tussauds in London, a waxwork head starts out as a model made of clay. Once the sculptor's happy with it, the clay is coated with plaster of Paris to make a hollow mould. Hot, runny wax is poured into it. The liquid seeps into every nook and cranny. After several hours, the wax has cooled and solidified. Eventually, the wax is hard enough to break off the plaster, revealing a lifelike head. Well, it will be with the addition of a couple of eyeballs and a bit of hair. So, what's happening to the wax particles as it melts? In a solid, the particles have very little energy. They hardly move at all. Warm it up and the particles gain energy. Eventually, they have enough energy to break free of the fixed arrangement and move around much more. A solid becomes a liquid at a temperature known as its melting point. These three cones are made up of different substances. They're all frozen in a cabinet which is at -25 degrees Celsius. Linseed oil on the left, water in the middle, and chocolate on the right. At -25, they're all solid, but as the cabinet warms up, the linseed oil begins to melt at about -20 degrees Celsius. It takes several minutes. When all the oil has melted, the temperature of the cabinet is increased. There's no surprises that at 0 degrees Celsius, the ice is the next to go. The chocolate finally melts at 25 degrees Celsius, the temperature of a hot summer's day. Some substances need more energy than others to melt. Aluminium melts at 660 degrees Celsius. Recyclers melt down drink cans and produce huge metal ingots. This one will make 1.5 million new aluminium cans. Even solid rock will melt. Molten lava spurting out of volcanoes is around 1,000 degrees Celsius. Steelworks rely on melting too. Temperatures as high as 1,550 Celsius are needed to melt iron. Solids need energy to melt. Iron needs a lot of energy, but at the other end of the scale, ice needs very little. The energy which makes these ice cubes melt comes from the surrounding liquid. What will happen to the temperature of the drink? A small ice cube needs very little energy to melt. But what about a much larger block of ice? which will melt first. And while you're thinking about that one, here's a look at ice through the centuries.
In Roman times, Emperor Nero ordered slaves to collect ice from mountaintops. They travelled miles in high-speed chariots simply to cool his favourite drink.
I don't know.
Uh-oh.
I'll have 2 more.
Before fridges were invented, ice was expensive stuff that only the very rich could afford. In Britain, it was cut from frozen lakes in winter and kept cool in underground ice houses until summer. Ice was so rare, it was even imported in huge lumps from overseas.
Look out!
Oh! The first Brit to investigate refrigeration was a man called Francis Bacon. In 1626, he stuffed a chicken with snow to see if the meat would stay fresher longer. But unfortunately, he caught pneumonia and died before finding the answer. In 1916, American businessman Clarence Birdseye pinched the idea of freezing food from the Inuits. He saw that fish buried in ice were thawed out months later and still good enough to eat. Mr. Birdseye had an idea. He started his own frozen food company, and the rest is history. The development of the fridge freezer finally meant that ice became available to everyone.
A few minutes later, and it's obvious that the large block of ice will take many more hours to melt. So, no wonder it was possible to ship ice from abroad in times gone by. Nowadays, we take ice for granted. Before the refrigerator was invented, ice sports could only be played when the weather was cold enough to freeze lakes and rivers. But it isn't long before the surface of the ice rink is chewed up and uneven. This machine repairs the surface by shaving off the damaged top layer and pouring on water. As it freezes, it gives the rink a new, smooth surface. But how is the rink kept cool enough to stay solid? Well, one way of keeping things cool is to put them next to something which is even colder. Liquid nitrogen is extremely cold and has to be handled with care. Place almost anything into it and it freezes immediately. Stretchy rubber gloves become as brittle as potato crisps. A banana freezes so hard, well, you can see for yourself. This is mercury. At room temperature, it's a liquid. What do you think will happen? But keeping things cool by immersing them in liquid nitrogen isn't very practical. On a hot day, you can keep a drink cool by draping a damp cloth over it. It works because the liquid water in the damp cloth is evaporating. It's gradually changing from a liquid to a gas. When a liquid changes into a gas, it needs energy. The liquid in the cloth takes energy from the bottle, so the drink inside cools down. The ice rink uses the same principle. Pipes underneath the ice contain a liquid which evaporates easily. As it evaporates, the liquid takes energy from the ice, keeping the ice cool. When a liquid changes into a gas gradually, like a puddle drying on a warm day, it's called evaporation. When it happens more rapidly like this, we say the liquid is boiling. The particles in a liquid tumble over each other, heat it up, and eventually the particles have enough energy to escape. The liquid breaks up and becomes a gas. In a gas, the particles move as far away as possible from each other. Gases take up far more space than a liquid. In fact, 1 litre of liquid water expands to fill 1,700 litres as a gas. So, what makes popcorn pop? Tiny amounts of liquid water trapped in each kernel suddenly expand. It changes from a liquid to a gas and makes the corn explode. A thermometer in a beaker of vigorously boiling water reaches 100 degrees Celsius. This temperature is known as its boiling point. However hard you heat the liquid, it won't get any hotter. But not everything boils at the same temperature. This is margarine. It boils at around 120 degrees Celsius. Again, the temperature won't get any higher. Liquid nitrogen boils at a much cooler temperature. Even on a tray of ice, it boils and quickly disappears. The opposite of boiling is condensing. This balloon is full of air. Plunge it into liquid nitrogen and firstly the rubber freezes, it becomes crispy. But what's happened to the gas inside? The air has changed from a gas to a liquid. You can see it collecting in the bottom of the balloon. The invisible gas has become a visible liquid. That's what happens when you breathe onto a cold piece of glass. The invisible gaseous water particles in your breath become a visible liquid.
All things, all stuff, all bits and bats, all clutter and all clatter, it all amounts to 3 things. 3 phases of matter. See, you hold a solid cup and you pour the liquid milk. But if you boil the liquid milk in the solid pan, then what comes to pass is neither solid nor liquid, but gas. See, it matters, does matter. Solid, liquid, gas.